Okay, so last time we finished the discussion of sonar, basically closed that chapter. We finished talking about CTFM, continuous transmission frequency modulated sonar. We talked about the DSP. We also talked about how you detect direction of arrival in ultrasonic sensors. Now we're talking about radar. As usual, you know how it goes, right? So we start from the physics, and here the physics is physics of electromagnetic waves. We started talking about Maxwell's equations. So these four equations basically govern the behavior of all types of electromagnetic waves and radiations, whether in radio frequency or in optical frequency. So this is how everything is at the physics level behaves. So what we can do from this is there is a very interesting mathematical theorem that says, and this is pure math, it's not physics. It says if you have a vector field which is divergence free, so if you have some field, vector field F, whose divergence is equal to 0, then that field can be written as the curl of some other vector field. And the reason is that the divergence of the curl of any vector field is always 0. So if you have some field that whose, well, I should call this something else. Let's call that A. So if you have some F whose divergence is 0, you can write that as the curl of some other field. So we can do that for our basically magnetic field H, because from Maxwell's equations, we know it's a divergence-free field. So we can write that as the curl of another field A, which we call the magnetic vector potential. Okay? Now, for this field A, to fully describe any vector field, either you have, you know, a explicit description of it, or if not, you need both the curl and the divergence to fully describe what the field is. So for A, the divergence is given by this, okay? And then we are free to choose what the curl of A is. Okay, and this peculiar choice here, which sets the curl of A to be equal to minus mu times epsilon times the time derivative of V, where V is the electric potential. Remember, the electric potential is like the integral of the electric field. So why make this choice if you're free to choose any value for the divergence of A? Because it turns out that this choice, when we plug this A to the Maxwell's equations, really simplifies the math. A bunch of terms cancel out with this choice of divergence of A. And it's a famous choice, and it's called the Lorentz condition, or the Lorentz gauge, that you might have heard of. So now what we can do is we can plug this A into the Maxwell's equations, and then after some simplification, especially using the second equation, we end up with the famous electromagnetic wave equation for the vector potential A. Okay? And the wave equation is written here. So we have the Laplacian of A minus 1 over c squared, where c is the speed of light, times the second time derivative of A equals minus mu times J. And remember, mu is a constant. That's the permeability of the medium. And J is the electric current density in units of amps per meters squared. Okay? Now, this should strike very familiar, especially from when we were discussing the acoustic wave equation. It was essentially the left-hand side was exactly the same as this. If you remember, instead of A there, we had P, which was the acoustic pressure. And instead of C, we had V, which was the speed of sound. Here we have speed of light. Right-hand side there was 0, but here also, if we are basically solving the so-called homogeneous version of this, where there's no current density in the space, then your right-hand side would be 0, and then you get exactly the same wave equation as the acoustic wave equation. And it should make sense, because these are waves at the end of the day, and the physics of the waves are the same, whether they're in like pressure waves in air or electromagnetic waves in free space. And it's the same type of physics. So it makes sense that the wave equation is the same. Also worth noting that there is a this famous relationship between the speed of light or the speed of electromagnetic radiation and the two constants, which is the epsilon and the mu, the permittivity and the permeability of the medium, which is C equals 1 over the square root of mu times epsilon. These are the three parameters are not all independent. If you know your mu and epsilon, that kind of determines what the speed of light or the speed of electromagnetic wave propagation is going to be. Any questions? Okay, as you go through this, just make sure on the math side of things, these partial derivative operators all, make sense to you and you know what they are. So we have a few now, right? So we have the divergence, right, of say A, and we know that's like the sum of the partial derivatives. So of A. I mean, I'm not going to rewrite it because they're given in the previous slide, but that's the divergence, right? Then we have the curl. And now in the next slide, as part of the wave equation, we also have the Laplacian. This is the vector Laplacian because A is a vector field, right? So A is a vector field, so it's in R3, so it has a x and a y and a z component, right? So there's an ax, there's an ay, and there's an az. And that's the difference. When we were talking about acoustic waves, the pressure was a scalar quantity, right? So there was just one value. But A is a vector field, so it has x, y, z components. And the Laplacian here is the so-called vector Laplacian. So what this is equal to, Snabla squared A, is the Laplacian of AX, Laplacian of AY, Laplacian of AZ. And this, we defined it when we were talking about acoustic waves. So just make sure, the math kind of makes sense, and what's a scalar, what's a vector, what do these partial derivative operators do? They should all make sense. Okay, so now we need to solve this, right, to find our A. How do we solve it? So to solve that, what's important here, if I clean this up a little bit, is so if you have some current distribution in some part of this space, if you have a J that is non-zero and it varies with time, if you have a time-varying J, that will give rise to the time derivative of A being non-zero. And that is the definition of radiation. When you have time-varying fields in free space, that is electromagnetic radiation. So to induce electromagnetic radiation, essentially what this equation is telling us is you need time-varying currents. And not everywhere, but at some part of the space, if you have some time-varying currents, then it will induce electromagnetic radiation. Now, what the radiation field is going to be, to know that, we need to solve this equation. And now we are going to do that. So the solution actually turns out to be quite simple, at least mathematically. And the way it's done is assume you have some current distribution in electric current distribution in some part of this space. So here we're making it very general. So this kind of like blue shaded bean-like part, that's like some part of the 3D space where there's some current flowing inside of it, okay? And then we are observing the magnetic vector potential A at some other part of this space, okay? So we're calling V prime the volume in which there's current flowing, and points inside that volume, the coordinates of them, we're denoting as R prime. So R prime is X prime, Y prime, Z prime, and those are the points inside this blue volume. And then we're observing our A at some point in the space R. So R is X, Y, Z. And again, R prime is kind of like limited to this part of the space that we call V prime, that volume. But R can be anywhere. So you can observe your field wherever you like. Even inside V, R can be inside V. That's also fine. And also things are varying with time. So both your current density is a function of R prime and T, and A is also a function of R and T. And now it turns out that there's just one integral that you need to evaluate, or solve in order to find your magnetic vector potential A. So A at a point r at a time t is given by this integral. There's a constant, mu over 4 pi, and we're integrating only where there is current. So only inside this V prime volume you're integrating. And what are we integrating? We're integrating basically the current density divided by R. What is R? R is at any point inside V prime, let's see that's some point R prime, the distance of that point to our point of observation, that is R. So R is the norm of little r minus little r prime, the two vectors, and that gives you the distance from where you're basically where J is inside the integral and where your observation point is. So that's in the denominator, and then the numerator J at point r prime, and then here's the interesting part. So the time in there is t minus r over c. And r over c, if we call that tau, what is that? That is the time of flight delay from that point r prime to point r, right? That's a distance divided by the speed of light, which intuitively should make a lot of sense. So if I'm observing my radiation at some point in space, the influence of some current distribution a distance r away from it, it takes a time of flight tau to affect that, my observation point, right? So that's why the time basically inside this integral is t minus rc, because it takes time tau for a changing current to be felt a distance r away basically from it. And so you just do that integral. You can do it numerically if usually J is known, okay, and the volume V is known, and then you can numerically do that integral. This d cubed r prime, if you're not familiar with this notation, that's just like a differential volume element, so it's equal to basically dx prime, dy prime, dz prime. That's what it is, okay? So this is fine, very general, no assumptions here. This always works, right? Any current distribution, any V prime, you know, this is like as fundamental as it gets in terms of finding electromagnetic radiation. But it's a bit annoying to solve this. I mean, you need to keep track of time and then delay your time. And of course, you could do it numerically, and it always works. But we like a simpler, solution, maybe with some simplifying assumptions that is more tractable mathematically. And to do that, we start with the usual assumption that we've made previously. And one thing that helps is that if the electric currents that are basically inducing radiation, we assume that they are single frequency or time harmonic, which is a valid assumption most of the times. So then basically you can decouple the time dependency of J from the spatial dependency of it. So you can write your J of r prime as t and t as some J of r prime times the time dependency is just a harmonic function, which is this complex exponential e to the j2 pi ft, where f is the frequency of basically the excitation, and it's related to the wavelength of the radiation via this formula. F is c over lambda. C is the speed of light, lambda is the wavelength, and f is the frequency of the radiation. So with this assumption for J, our A, the magnetic vector potential, also becomes time harmonic. So our A of r and t, also we can write it as some A of r, so that's the spatial dependency of it, and the temporal dependency is just e to the j2 pi ft, which is a pure harmonic. Now that very general integral we had in the previous slide can be simplified for this case. And the reason it can be simplified is because our wave equation becomes much simpler. So the magnetic wave equation for the harmonic case, well, the Laplacian of A, that's still there. But remember, we had this 1 over c squared second derivative of A t squared. That term simply becomes just a constant times A. And that constant is the square of our wave vector, which is 2 pi over lambda. And the right-hand side is still minus mu j as before. And this new equation, the simplified one, has a simple solution. So now we only have to solve for A of r, because the temporal part of it we already know. Okay, so now we just need to find A of r. And then A of r, so the amplitude, or the complex amplitude of the magnetic vector potential at a point r in space is now given by this integral. You still have the mu over 4 pi constant behind the integral. You're still integrating over v prime, which is the volume that contains the current. But now the integrand is much simpler. So you have j of r prime. That is just your current distribution at a point r prime inside this v prime volume, multiplied by this term. This should be very familiar to you. E to the minus j norm k r over r. What does this remind you of? One. You've seen this when we're talking about acoustic waves. Remember spherical waves? It is a spherical wave. That's the definition of a spherical wave. A wave where has a constant phase on a spherical surface is always given by an expression like this. So whenever you see something like e to the minus j norm kr over r, you should be kind of on your toes because you know what it is. It's a spherical wave. So what we're doing here, and then we're again integrating over the volume. So this integral here intuitively should make sense because essentially what we are doing here is very similar to, remember when we were talking about acoustic waves, we described this Huygens-Fresnel principle, which said if you have some aperture emitting waves and you want to find your radiation at some distance away, you can break down your aperture into points, each of which is emitting a spherical wave, and then you sum up the contribution of all those spherical waves at the point of observation, and that gives you your full field or radiation at that point. Here, essentially, we are doing the same thing, right? So j of r prime is just like how much current you have at point r prime, and we are multiplying that by this spherical wave term, right? And we are integrating them, and that is our magnetic vector potential at point r, right? So that's exactly what we are doing. So again, if this is our volume v prime, at every point we are assuming every point is, radiating a spherical wave, and then there's this point r at which we are observing, so we are summing up the contributions of all these spherical waves at point r via this integral, and that gives the full field for us. So again, it's essentially the core idea here is the same as the Huygens-Fresnel principle that you've seen before. Okay, so this is good, right? Now, essentially, for any v prime or any antenna shape, if you want, or geometry, we can find the magnetic vector potential. But the quantities we are really interested in are still the electric and magnetic fields, because as we see, a lot of like physical quantities like how much power you radiate, what is the pattern of radiation, and all that are directly related to the E and H fields. So from A, we still need to find what is the E field, electric field, and what is the H field, the magnetic field. It's very simple. Once you have solved for A via that integral, we can find E and H from it very simply. Basically, H is just you take the curl of A and divide by mu, because by definition, we had defined A or curl of A, remember, to be, not divergence, sorry. The curl of A we defined to be mu H. So H is easy. E is also kind of easy, but you need to plug A into the Maxwell's equations and do some simplifications, but it turns out that it depends on A via this equation, which is minus j omega A. Omega is the angular frequency, so it's just 2 pi times the frequency in hertz, minus this other term, which is j over omega mu epsilon times the gradient of the divergence of A. Okay? Okay, let's make sure this makes sense here. Okay, divergence of A, we know what it is, right? And the divergence of A is a scalar quantity, right? A itself is vector, but the divergence of a vector field is a scalar field. So divergence of A is just a scalar field. And then the gradient of that, generally the gradient of some vector field F is equal to basically partial f, partial x. It's a vector, right? Partial f, partial y, partial f, partial z. So the gradient of the divergence, this bigger term, is again a vector in R3. Just making sure our derivative, partial derivative operators here make sense, okay? And E is, of course, a vector field minus j omega A is a vector, and then the gradient of divergence of A is also a vector. So dimensionality should make sense here. Okay, so we can find A for any antenna essentially, or any shape in space with some current in it, could be an antenna. And then from that, we can now find our E and H fields. Good, we're making progress. The first thing we're usually interested in is power, right? How much power are we essentially, or what is the power density that we are radiating? And that is directly proportional to both E and H field via what is called the pointing vector. So what the pointing vector is a vector that gives you the average power flux density. What is average power flux density? So first let's look at the math. So S average is 1/2 times the real part of the cross product of E and H star. So you have to conjugate your H field and take the vector cross product of that with E, and then the real part of that is called the pointing vector, and the units of it is watts per meters squared. So it tells you basically per unit area at some point in space how much power flux is going through it. So if you kind of like look at a square of area 1 meters squared, the total electric power that is going through that would be equal to basically the magnitude of S average. So that's why S is watts per meters squared. It's like the flux density of the power, which is very important, right? Because when you're sensing, you need to know how much power you're radiating and how is that power distributed in the 3D space. And we'll talk more about that. So if that volume that is where the current is contained in the case of a radar, we call that the radar antenna. Okay, so the antenna is where the current is flowing, and that's the source of the radiation. Then the pointing vector basically gives the radiation power density of your antenna, right? It tells you around the antenna per unit area how much power is flowing out. So say you want to calculate the total power that your antenna is radiating. What do? If S is power per unit area, you can integrate that over a enclosed surface that encloses your antenna. If you integrate that S over the full surface, that gives you the total radiated power. So here's a picture kind of showing you how that is done. Let's say this big sigma is the surface. It can be of any shape, right? Here it's like fancy looking, but it could be like a sphere, where your antenna is inside that, and you want to find the total power that is radiating out. What you do, so your radiated power would be the integral of S over this surface, but what you want is the power that actually is going out of this surface sigma. So you have to take project S into the normal direction of the surface. Why is that? So this S dot n hat, what it does, let's first see what is what. So S is a vector here shown in red, and that shows in what direction power is flowing and what is the density of it in watts per meters squared. Now if you look at a small basically surface element on this bigger surface sigma. Let me highlight that in green. So that is our ds. That's a small element of surface. So that element is going to have a normal vector which we call n hat. Okay, and when we do the dot product of S and n hat, that basically gives us the component of S that is in the n hat direction. So the projection of S in the n hat, and that is basically the power that is flowing out. Why do we do the dot product? It's kind of, I want to make sure that makes sense. If this was, I'm just going to show a 2D version of this. If this was an element of the surface and this was the n hat That is the normal vector to it, normal unit vector. But our S vector was orthogonal at that point. If our S average was like this, well, that power is not flowing out of the surface, right? It's just going tangential. So we don't want to include that in our total radiated power. That power is still contained in the surface. So that's why, and that is taken care of by doing this S dot n hat, because in this case, S dot n hat is 0, and that orthogonal component of S does not contribute to this power that we are calculating. So the projection is important. You project your Poynting vector into the normal direction at every point ds, and you integrate over the volume, and that gives you your total radiated power. In terms of E and H, again, S is 1/2 the real part of E cross H star. Okay, so you see, we can do, we're not just doing physics. For physics, these are real quantities that matter that can be calculated from these electric and magnetic fields. Okay, so just like acoustic waves, electromagnetic waves also get attenuated as they propagate in air. Okay, remember in the case of acoustic waves, we talked about this Stokes' law of attenuation that told basically higher frequencies get attenuated more than lower frequencies. And that kind of determined what was the range of frequencies that was useful for sonar sensing in robotics. Same idea applies to electromagnetic waves. It's not governed by Stokes' law, but nevertheless, there is attenuation at different frequencies. So this plot here, x-axis is the radiation frequency in gigahertz. So we're going from 10 gigahertz to a few hundred, 350 probably. And then the vertical axis is attenuation factor in dB per kilometers. And as you see, the general trend is higher frequency, higher attenuation. But there are some basically very sharp peaks at specific frequencies. These peaks are due to absorption of different molecules that are in air. So air has oxygen in it, it has nitrogen, it has some water content, it has CO2. And those molecules have basically resonances at very specific frequencies, and if your wave happens to be at that resonance frequency, a lot of its power is going to be absorbed by those molecules. So this, for instance, here could be a resonance of the H2O molecules of water. So those are bad choices for radar, right? Because you suddenly get a lot of attenuation. We don't want to be too close to those peaks. Now, specifically for radar in robotics, the two frequencies or two frequency bands that are very commonly used, one is this one, which is between 24 and 24.25 gigahertz. And that is part of the so-called K-band according to the IEEE standards. And then we have this frequency band, which goes from 76 to 81 gigahertz, and that falls inside the so-called IEEE W band. Okay? Those are the most common ones for radar and robotics. Radar in general, a lot of other frequencies are used, as I'll show you in the next slide. But for robotic application, these types of radars that we'll talk about, these are the most common ones. More modern ones are at 76 to 81. 24 gigahertz radar, it's kind of getting phased out because the performance in terms of the resolution and range is not as good. Usually higher frequencies are better. You get better resolution, better sensitivity, and so on. Also, you can work with smaller antennas at higher frequencies. So higher frequencies are generally desired for radar. Although there's more attenuation, but for other reasons, it's desirable to work at higher frequencies. Now, if you look at, radar in general, not just for robotics, like as you know, radar is used in tons of different applications. Many different frequencies are used, and different frequencies are good for different applications. So this picture here, what we have is, we're kind of looking at a very broad range of frequencies. So you have frequency here on the top, which is going from a few tens of megahertz all the way to hundreds of terahertz, which is not even RF anymore. That's basically optical frequencies and beyond. At the same time, we're also showing wavelength for comparison. And remember, these two are related, right? So F is equal to C over lambda. So we're also showing wavelength, which is going from hundreds of centimeters to basically sub-micron as we span these wide range of frequencies. And here, different frequency bands, there's naming conventions for them. And IEEE has their own standard, and also NATO has their own. NATO's is much cleaner. It's just alphabetical. They go A, B, C, D, E, F, G. Very easy. So for instance, the B band in NATO goes from like 1/4 gigahertz to 1/2 gigahertz or something like that. IEEE is a bit of a mess because it was historical. As they, new frequency bands became available, they kind of like started adding to it. So it's like HF and high frequency, VHF for very high frequency, UHF for ultra high frequency, and then they ran out of, what to add to HF. So then they called it L, and then there's S, X, K. I mean, I really don't know who came up with this and why, but that's the IEEE standard. Now, not every frequency can be used. That's very important. Electromagnetic spectrum is a very precious national resource, and it's highly, highly regulated by the FCC, which is the Federal Communications Commission or something like that. In the US, other countries have their own governing bodies that decides what frequency can be used for what application. Because if you just open everything to every application, you're going to have a ton of interference, of course, and nothing works, right? So everything is highly, highly regulated, not just for radar, like for our communications, like Wi-Fi has very specific frequencies, LTE has a specific frequencies, now 5G has very specific frequency bands. There's like medical applications, military applications, a lot of applications. So if you look at, go on the FCC website and check the electromagnetic, allocation, spectrum allocation, it's tightly packed. There's almost, nothing left out to basically give out. So for radar, for different types of radar, these bands highlighted in light green, those are for different types of radar. So you see, for instance, ground penetrating radar operates at very low frequencies. It's like sub-gigahertz. And then, I don't know, like your airport surveillance radar operates in the IEEE S band, which is between like 3 and 4 gigahertz. The ones we're interested in, again, is the K band. That's the 24 gigahertz. That is useful for robotic applications. And the most interesting one now is basically this here, which is our 76 to 81 gigahertz band, which is now the most modern types of radars for autonomy use that frequency band. Body scanners that you see in airports, they operate at around 100 gigahertz, so these are even higher frequencies. Next one now, so every few years as the technology makes progress, higher frequencies typically get regulated for radar applications. Next one that, in the research community is really pushing for to open up for these types of high-resolution imaging radars is around 120 gigahertz. So hopefully in a few years, we'll see something open up here, and we'll see, a new generation of radars at even higher frequencies. There's a ton of research already being done on it. So in academia, there is radar systems that operate at those frequencies. But of course, you can only use that in a lab. If you take it outside and FCC finds out, you can get big fines for it. Okay, so that's that. Just to recap, so these two are today the ones that are mostly used for robotic radar. State of the art today is this frequency band, 76 to 81. Why is it better than 24? There's different reasons. Of course, you get a little bit more attenuation, but that's not the big deal. We can deal with that. You get larger bandwidth, of course. right? This is just a quarter of a gigahertz available here versus here you get like 5 gigahertz. That's good. You get smaller form factor because, as we'll see, antenna dimensions is proportional to the wavelength. So as you go to from 24 to 76, your wavelength, your antenna dimensions become almost 10x smaller. And you also can transmit higher power. Again, FCC has allowed us to radiate more power at 77 or at 76 to 81 gigahertz band, so you can transmit up to 55 dBm versus in 24 we could only do 20 dBm. These numbers are not universal, so you go to Japan, these numbers are going to be different because every country regulates their spectrum a little differently. But today I think 76 to 81 is globally open for imaging radar applications. I think there's been agreement on it. And then, as I said, 120 to 140 gigahertz hopefully is a very active area of research, and hopefully in a few years it's going to be officially available for commercial use. I mean, I've also seen like in research people working on like 300 gigahertz radar and beyond. So at those frequencies, as you get close to terahertz, things become really interesting because the line between, you know, what's RF and what's optical kind of becomes blurry at those frequencies, and you can do very interesting stuff. Okay, any questions? All right, so at a very fundamental level, this picture you've seen before, this is the principle of operation of a radar, which is exactly the same as the principle of operation of an ultrasonic sensor, right? So you have a transmitter and a receiver. In the case of sonar, we call it a transducer. For radar, it's called an antenna. It sends out, it transmits some wave, shown in red here. It hits a target, and then target echoes back part of that electromagnetic wave that hits it, and then the receiver receives that reflected echo and processes that signal to determine a few things. The two most essential ones is the range to the target and also the direction of the target, which is called the bearing angle or the direction of arrival or the angle of arrival. So those two need to be determined. Range is determined by the time of flight principle. So if the round trip time of flight is tau, then your range would be, as we know, speed of light times tau over 2. Why over 2? Again, because it's round trip, but our range is just a one-way range. And also, with some more processing, the radar can determine the direction of arrival. And also, we'll see, it can also find the radial velocity of this target. So if this target is like moving away at some velocity v, or coming towards the receiver at some velocity v, radar can determine that based on the Doppler effect. Okay. So that's the picture, and this is also why it's important to understand the physics. Again, the way we approach these sensing problems is, first, it's this picture, right? This is like the 10-second description of how a radar works or how a sonar works. But if really we want to get deep and get a deep understanding of how they work, we first start with understanding the physics. Like, okay, this wave that's being transmitted, what does it look like? What characteristics does it have? What, you know, in terms of the beam pattern and the power that it's transmitting and all that, what does it look like? Then we look at, okay, what is the echo that comes back? Okay, we also study that at the physics level. We also need to understand the transmitter and the receiver. Like, what is the behavior of those, exactly as we did for the case of sonar. And once you understand all the physics here, from the transmitter, transmitted wave, the echo that comes back to you and how you receive that, collect that echo power, then we can build a full signal model, right, for our system. And then from the signal model, then we can look at the signal processing. How do you process that signal to extract what you're interested in, which is range, which is direction of arrival, and velocity. So again, I hope this justifies why we go into the depth of understanding the physics, because without the physics, this picture is just a picture. There's nothing actionable that we can do on it. It's only after we study the physics that we can do something actionable. And the actionable thing is that to build a very realistic signal model that then we can talk about the DSP on it and really understand how the sensor works. So the next thing we're going to study, we talked about, electromagnetic waves and how they propagate Maxwell's equations. So right now, if an antenna geometry is described for you, essentially you can find the E and H fields that are radiated from it. How do you do that? First, you do that integral that finds the magnetic vector potential A from the current that is on the antenna. And then from A, you can find your E and H fields, and that is basically your radiated electromagnetic field. Now we're going to talk in detail about antennas, right? What is an antenna, and how is how does some of the properties of these radiated fields determined by what the antenna is? Okay, so what is the antenna? At a very high level, the antennas are the interface between the waves that are getting radiated and the basically electrical currents that are inside the circuits that make the radar. Okay, just like the case of sonar where we had transducers that could both transmit and receive signals, antennas are the same. They can transmit signals, they can also receive signals, so they can operate basically in either direction. There's many different types of antennas, and this kind of like 4 pictures here, this is not the exhaustive list of like all types of antennas that are out there, but these are some of the common ones that are used for radar. So you can have dipole antenna, which is basically just 2 wires. You can have the so-called reflector antennas, which are these dishes. We have a giant one here on the hill at Stanford that I'm sure you've seen. You can have horn antennas, and you can have what is called microstrip antennas. And for robotic sensing, the most interesting one is the microstrip antennas. Why are these very interesting? They have several really good properties that make them really interesting for these applications. First, they are very easy to make. I mean, these antennas are just basically some copper pattern on a PCB, on a printed circuit board. Here, this picture is actually showing 6 antennas. You see, each of these is an antenna. So you have 2 on this side, and then you have 4 on the right side. Okay? So very easy. You can, generate any copper shape that you want. Also very cheap, because PCBs manufacturing is extremely cheap these days. They don't take up a lot of space compared to, like a horn antenna or a reflector antenna. And also, what makes them perhaps the most desired property is this one, which is you can place many of these microstrip antennas on just one PCB. So you can make a full array of them in a very small form factor. And we will see later why this is important, why having multiple antennas. But just to give you an idea, with multiple antennas, we can have much better resolution in determining the direction of arrival. So your basically angular resolution becomes much better when you operate with multiple antennas. I brought a couple of these to just show you if you want to see them up close. This is a horn antenna. It's exactly the same one that is on the slides. And if I can take it out without breaking it, this one is a array of microstrip antennas. Again, it's the exact same one that you see on the slides. So a couple of things. So these are for 24 gigahertz, right? I didn't have one for 77 at hand to bring, but a 77 gigahertz antenna would be much smaller. It would be almost like, in area, it would be 1/10 of the size of the 24, because antenna dimensions are proportional to wavelength. Now, these two, if I put them next to each other, like the aperture opening of the horn next to this antenna, you would see they're almost the same dimension. if I can show it correctly. Not a perfect match, but they're very close. And that's not a coincidence. That's because these are for the same frequency, and the dimensions of your antenna have very specific relationships to the wavelength, so that's why these are roughly the same. This one, the microstrip, it's not just an antenna. So on that same PCB, if you look at the back of it, you have your full radar circuit. You have the transmitter, there's a DSP chip here, there's everything. So it's the full radar system versus this one is just an antenna. It has basically a coax SMA cable feed, so you have to like feed the signal to it. And it's just one antenna. This one has 6 antennas, 2 transmitters, 4 receivers, plus your entire circuit, and it takes a lot less volume than this guy. So that's why these are very desired for robotic applications. Anyone wants to see these? Yes? No? Pass them around if you want to see what they look like. Okay. So here's another very interesting one. It's a radar system made by a company called Arbe Robotics. And it's a PCB roughly the size of the one that you have. You would see it's slightly bigger, but not a lot. Maybe like 1.5. And this one has 48 TX and 48 RX microstrip antennas, which are basically what is highlighted here, and up top. Plus all the electronics, everything integrated in one PCB. And this is a huge array, right? You get like almost 100 antenna elements on one PCB. So again, that's why microstrip antennas are so interesting and desired for these applications. Now, when it comes to antennas, there are different regions of radiation, as we call them. So there is a near field, and there's a far field. Near field is if D is the largest physical dimension of an antenna. So for instance, for the horn antenna that you have, D would be the length of the horn. Or for the microstrip antenna, it would be the length of that microstrip. So if D is the largest physical dimension, near field is where your distance to the antenna is less than 2d squared over lambda. That's the near field. And the far field is if your distance is bigger than 2d squared over lambda. What is the difference? Why do we care? When you're in the near field, the radiated field is approximated as spherical waves. And when you get to the far field, you can approximate your radiated field as plane waves. So graphically, this is what it looks like. So if you have some source that is feeding a transmission line, so this part is the transmission line, like a coax cable or something, and then it's feeding an antenna. So the antenna, in this case, we are showing something like a horn antenna, right? So what happens is that your electric field is contained inside the transmission line, and then it gets coupled to the antenna. So these arrows are the electric field lines. You're showing like a 2D cross section, and then when it gets to the basically aperture opening of the antenna, fields start to radiate out. In the near field, the fields are kind of like curved and spherical looking, so that's your near field. And when you get to the far field, I mean, it's still kind of spherical, but as the sphere becomes larger and larger and larger, locally, it just looks flat. So that's why at far field, you can approximate your field lines as just flat, and they're just plane waves. Now, one thing to note is, again, we call this far field, but really it's not that far away from the antenna, at least for the frequencies that we work with. So let's say you're at 77 gigahertz, okay? At 77 gigahertz, very ballpark, let's just do like a ballpark calculation. Your D would be about 10 millimeters probably. I mean, most antennas are roughly on that order. Okay, and what is lambda? Lambda is about 4 millimeters. Again, numbers are not exact, but rough. Ballpark, okay. So plug those in. So what is 2d squared over lambda? So 2d squared over lambda would be, what, 200 over 4, so it's 50 millimeters. So if you're 2 inches away from your antenna, you're already in the far field. So it's called far, but it's not like meters far. It's tens of millimeters far away, at least for the frequencies that we will be working with. So all of our analysis, everything is going to assume far field. It's very important to know. from here on, we always assume everything is in far field because for robotic applications, those are the typical scenarios. Now, having said that, if you are working on an application where it's near field, well, everything we say wouldn't necessarily apply, so you have to, correct those assumptions. But it's absolutely not the case that radar does not work in near field. There is near field radar, and they actually work beautifully, but the signal models are different, the DSP is different, the physics is a little different. Okay, so far field radiation, what we get with that far field approximation, called that the electric field at far field and the magnetic field. Let me actually show the picture also here. So the electric field at far field, we can break it down into the full, spatial dependence of it. We can decouple the range dependency from the angular dependency. So the angular dependency, call that E of theta and phi. And here we're working in spherical coordinates. So the spherical coordinates, the way it's parameterized, as you know, you get a radial distance, r, to any point. So this is a point in space. So it has a radial distance, r. And then there's two angles. Theta is kind of like your azimuth angle, and phi determines your elevation. Okay? So theta, phi give you just the direction, and r is how far you are, basically, in the spherical system. So your electric field at point r, we can write it as E of theta and phi, so that's just, the directional dependence. And the range dependence, as we said, is just a spherical wave. So it's going to be this term, again, that should be extremely familiar to you, which is e to the minus j, norm k, norm r over r. So that, again, is your spherical wave. So here we are assuming antenna is at the origin, of course, right? So if we put the antenna at 0, 0, and then we're looking at far field. And it's a vector, so we also need to determine what the direction of the vector is. So this unit vector here, E hat of E, that's kind of like what the direction of your E field is. H field, same thing. We can break it into some theta phi dependency, h of theta phi, times a spherical wave. And that also has its own basically direction, E hat of h. Now it turns out that the two fields, E and h, at far field, they're always orthogonal, okay? Which means these two unit vectors, E hat of E and E hat of h, are orthogonal. Okay, and they are also, again, the assumption here is that at far field, the fields are kind of like planar, so the direction of the travel of the wave, the plane wave, is r hat. Okay, so it's radiating out, and your two fields are going to be, your E and H fields are going to be in the plane that is determined by the theta hat and the phi hat unit vectors. So if I were to redraw it here at far field, you have this r hat, that is the direction of the propagation of the wave, and then in there you have some E hat of E and some E hat of H that are both orthogonal to each other, but also orthogonal to r, because the fields are traveling in the r hat direction. Also, more interestingly, it turns out that the amplitude of the E and H fields are basically proportional to each other in the far field, and that constant of proportionality is called eta, or the impedance of the medium. And eta is given by the square root of mu over epsilon. So just to summarize, your H field is just this 1 over mu term times r hat vector cross product with your far field E. Okay. Now at far field, if you want to find your power radiation intensity, which is the pointing vector, these assumptions that we just made makes the pointing vector very simple to calculate. So basically, the far field radiation, by definition, our S is 1/2 real part of E cross H star, right? But here we're looking at the far field approximate fields. We just said H at far field is 1 over eta r hat cross E, far field, right? So we plug that in, and what we get here is E cross R cross E star, right? Here there is very simple geometry. Again, remember that you have R hat, and E, or the unit vector that determines the direction of E, is orthogonal to R, right? So what happens if you do R hat cross E, right? If you do your right-hand rule, that gives you another vector which is also orthogonal to both E hat and R. Okay, and that actually is your E hat H. And then you do E cross that again, so the final product is going to be in the R hat direction. Does that make sense? So you do R hat cross E, that gives you another vector in the EH plane, and then you do E cross that, so you go back, the direction of what comes out of this two cross products is going to be in R hat. And what is the amplitude going to be? Again, by the fact that these are all orthogonal vectors, the amplitude, R hat has unit amplitude, right? And you know from the cross product, the amplitude of the cross product is amplitude R hat, amplitude E, times the sine of the angle. Sine becomes 1 because the angle is 90 degrees. So the amplitude just becomes the square of the amplitude of E, right? Because the first one just gives you a vector with the amplitude that is just norm EFF. And then the second cross product, you get E kind of cross a product which has the same norm, and they're orthogonal. So you get norm squared of E, and the direction is R hat. So norm squared of E, real part of it, it's a real quantity, right? The norm of any vector is real valued. So then the real part doesn't matter. We can drop it. And our basically power radiation, power flux density becomes just the square of the far field E divided by 2 eta, and it's being radiated in the R hat direction, right? If you would like to write it in terms of, remember we said our EFF is, it has some theta phi term times the square wave, spherical wave is J norm K norm R divided by R. So if you take the norm of this term is a pure phase, it becomes 1, and we are just left with this, which is norm of E of theta phi squared divided by, you get the R squared in the denominator, and the 2 eta just carries over. So that's our basically power radiation intensity, density at far field, right? Graphically, it looks like this. Maybe this makes it clear if it was confusing to you. Just to summarize, we are at far field, so we have our H at far field and an E in the far field. The two fields are always orthogonal, right? As it's shown here, the blue and the red are always orthogonal in the same plane. And there is this direction R hat, which is the direction of like how the power is flowing. So look at this here. So you have your direction of your H field, direction of your E field, and then there's R hat. And all of these are orthogonal to each other, right? Now your pointing vector, which is where the power is flowing, is E cross H, right? Or E cross H star. So it's going to, of course, if you do your right-hand rule on E and H, it's going to point in the R hat direction. So power is flowing in the radial direction, basically, at the far field. And the density is given by norm squared of E of theta and phi divided by R squared times 2 eta. The 1 over R squared term should make sense. Again, as you get further and further and further away from your antenna, the power density should drop kind of spherically, because these are spherical waves, right? So the 1 over R squared is kind of like proportional to the surface area of a sphere. So that's why you get a 1 over R squared drop in your power radiation. So just to summarize again where we are at. So we have this relationship between the far field, electric and magnetic fields, right? It's given by this 1 over eta times the vector cross product of R hat and E. What is eta? Eta is the ratio of the electric field amplitude to the magnetic field amplitude, which is equal to square root of mu over epsilon. In free space, if you plug in the value of mu and epsilon for free space, eta becomes 377 ohms. And that's the impedance of free space, the so-called impedance of the free space. And our far field radiation power density, S, is given by the norm squared of far field electric field over 2 eta, or explicitly in terms of the angular dependency of E, it's E of theta and phi divided by r squared, norm r squared times 2 eta. And power is always flowing in the radial direction. Okay? So that's basically where we are at. So let's see, like, why are we doing all this, right? Why going through the pain of all this physics and all the derivation? Again, so that if we go back to this picture, if I can find it, if we go back to this picture here, we are doing this because we are studying the physics of, like, if I put an antenna here which generates some electromagnetic field, and I have a target at the far field, for instance, what is the power that is hitting the target? What is the power density that's hitting the target? And then from that, hopefully, we can calculate what is echoing back. And when we have the echo back, we can calculate what signal we're going to receive on the receiver. So we are, again, not doing physics just for the fun of physics or for the pain of physics, depending on how you see it. We're doing physics so that we can understand how this sensor works. Okay, now from here, when it comes to antenna theory, basically your E and H field determine everything, right? Because that's physically everything that's there. There's electromagnetic radiation, there's an E field and an H field, and that's it, right? You don't need anything else in principle. But just to, for things to intuitively, become a little more digestible, there is a bunch of parameters associated with antennas, which are functions of the E and the H field. And we're going to, kind of go over those parameters and see what they are. But there's no new physics here. Basically, we're done with the physics. And the rest is just, some visualizations and some antenna parameters that are defined based from the E and the H field. The first one is the radiation intensity, also called radiation pattern or beam pattern. When we were doing sonar, if you remember, we calculated this acoustic beam pattern for a transducer, which had, a main lobe and some side lobes and some beam width. This is the electromagnetic equivalent of that. It's called U of theta and phi. So it's a function of the azimuth and the elevation angle, and it's the power that is radiated from an antenna per unit solid angle. Okay, first let's remind ourselves what solid angle is. So, well, what is a regular angle? So if you have a circle and you have some arc on the circle with length L, and the circle has some radius r, what is this angle theta here? Theta in radians is equal to L over r, right? And that's why a full circle is 2 pi radians, because the circumference of the circle is 2 pi r. You divide by r, you get 2 pi. Okay, so that's how regular angles are defined. Now, in 3D, if, say, you have like a sphere, and you have some area on the sphere, part of the surface of the sphere with area A, and the sphere has radius r, then you can define the solid angle here, which we call omega. And the solid angle omega is defined, so it's like the 3D analog of the regular angle, which is defined by the area A divided by the square of the radius. Okay, so area divided by the square of the radius, that's the solid angle omega. The units is steradians. Okay, so a full sphere has a area of, is it 4 pi r squared, right? So you divide by r squared. So 4 pi is the full solid angle of a complete sphere, compared to 2 pi, which is the full angle of a circle. So U of theta and phi is basically the power radiated from an antenna per unit solid angle. So if you look at kind of like a small area with a unit solid angle of 1 radians, how much power is radiating out? Okay, very easy to calculate. Why? Because we already have basically our Poynting vector S, which remember it gives us S gives us power in watts per meters squared, right? Now omega is basically the area divided by r squared, or norm r squared. By definition, that's the solid angle omega. So power per solid angle 1 over omega is going to be basically r squared over a. And the S is basically the P over A part. That's power per unit area. If we multiply that by r squared, that gives us power per solid angle. Very easy. So we know S basically was E squared over R squared. So you multiply by R squared, the R squared in the denominator goes away, and you're left with this expression. And now the units is watts per radian. So that's the radiation intensity or the radiation pattern. Now, what's nice about this is basically it removes that range dependency of it. Range, we know, there's always a 1 over R squared drop in power density, right? We take that out of the picture, and this U just tells us the radiation pattern as a function of azimuth and elevation. And you don't need to, say, oh, I'm talking about 10 meters away or 100 meters away. Take that out of the picture when you talk about solid angles, then you don't need to define like how far away you are, basically. And then from that, we can calculate basically, for instance, the total power radiated from an antenna. If you want to calculate that, you just integrate your power density over an enclosed surface over the solid angle omega. Right? If you want to do it with basically theta and phi, your azimuth and elevation angles, from geometry we know, element of solid angle d omega is sine theta, d phi. So then the integral becomes, you vary your azimuth angle from 0 to 2 pi, you vary your elevation from 0 to pi, and then you integrate your radiation pattern times sine theta, d phi. Okay, visually this is, for instance, what it looks like, and this should be very familiar. Like the radiation patterns, for instance, we looked at for acoustics, very similar, right? So here again we have like an antenna at the origin, and this 3D surface is showing this basically radiation pattern as a function of azimuth and elevation angle. We're normalizing it, so we're dividing by the maximum value just for convenience, just such that the maximum value is now 1 because it's normalized. It's just a nice thing to do. But basically, it's all the same concepts that we talked about in acoustic waves apply here. So you have your main lobe, basically. That's where most of the power is being focused in and radiated inside that. You have a bunch of side lobes. By the way, all these 3 pictures are showing the same thing. It's just different visualizations. You have like the full 3D surface. This one is like a cross section of it, right? For at a fixed, I think it's at a fixed theta or a fixed phi. And this one, it's just a 2D plot as a function of theta for phi equals pi over 2. Okay. But essentially same thing, right? Then you have your main lobe, you have your side lobes, and then you can calculate the width of your main lobe. There's 2 ways in radar that they code basically the width of the main lobe. Either they code it as a half power beam width, so that's way, if you've normalized the peak to 1, then this width is where it drops to 0.5. And that's one way of coding like how wide your main lobe is. The other one is how we did it for sonar, which is you take the 2 zeros, and this one is called full null beam width, or FNBW. And that's another measure of how wide your beam width is. Simplest antenna you can think of is called a isotropic antenna. And that's an antenna whose radiation pattern is like a perfect sphere. So it doesn't have any directionality, basically, or any preferred direction in which there's more power radiated. So this basically green sphere here shows you the radiation pattern of a perfectly isotropic antenna. It's like a perfect sphere. Important to note that isotropic antennas are never physically realizable. So there's no antenna geometry that you can build whose radiation pattern is going to be a perfect sphere. Anything you build is going to have some asymmetry in it. So isotropic antennas is just like the ideal case for mathematical studies. Every antenna is going to be non-isotropic, so it's going to have like a main lobe and some, side lobes around it. But what's nice for isotropic antennas, we can get close to isotropic, but not perfectly isotropic. The radiation total radiated power for isotropic antenna is very easy to calculate, right? Because the U of theta and phi is just a constant, right? There is no theta phi dependency. So you plug it into the antenna, you integrate U0 d omega. U0 comes out of the integral, so you're just integrating d omega over a enclosed surface. And as we said, for any enclosed surface, the full solid angle is 4 pi, just like the full angle of a circle is 2 pi. So the total radiated power for a isotropic antenna becomes 4 pi times U0. Or if you want, the radiation pattern, the amplitude of it, is given by the total radiated power divided by 4 pi. I think this is a good place to stop. We're out of time. Any questions? All right, I'll see you next time.